Okay, let's get started. Today we start this new course, Probability and Statistics. And for the record, let me mention that these lectures take place at the International Business School of Plekhanov, Russian University of Economics. And this is the name of the lecturer. The course will comprise 10 lectures that will be accompanied by practice classes, and you will be provided with handout materials and homework assignments sufficient to get you prepared for the exam. Well, I want to say at once that 10 lectures is a very limited time frame for this huge subject, and this limitation determines the style of the course. I will not have time to go into many details. I'll have to leave out many essential things and only address the main stuff, the basic stuff. Also, because these lectures are not designed for mathematicians, but for future businessmen, I'll not be going into any proofs. Rather, I see my objective in giving you an informal, intuitive understanding of the subject. And also, I'll try to supply you with practical methods that you'll be able to apply directly in your professional work. Okay. Now, what is probability theory about? Probability theory is a science that deals with uncertainty. Uncertainty. And uncertainty is something that we meet with everywhere and always, whatever we do. Every one of us meets with uncertainty in our everyday life. When a student takes an exam, there is always some degree of uncertainty as to the result. You may be well prepared for an exam and still fail because through some bad luck. Okay? On the other hand, you may be poorly prepared and still be successful because you get lucky. Okay? So there is always this uncertainty. When somebody starts a new business, there is a lot of uncertainty as to what's going to happen to this business. When a company launches a new product, it's always uncertain whether the product is going to be a success or not. On a global level, the global economy as well as the national economies are subject to uncertainty. Share prices, commodity prices, currency exchange rates are all subject to fluctuations. And this is not something marginal or some minor effect. It's the very essence of what's going on in the economy. Well, in social life and politics, well, whenever an election is held, there is some uncertainty or sometimes a lot of uncertainty as to what the result is going to be, who of the candidates is going to win. Now, we know that in the neighboring state of Ukraine, some very serious disturbances are going on. And I want to emphasize that only 2 weeks ago, nobody was able to predict that such serious and dramatic developments would take place. And today, nobody can predict with any certainty what these developments are leading to. Okay? So, political life is always about uncertainty. Well, in nature, such natural phenomena as earthquakes, the fall of meteorites, hurricanes, can hardly be predicted, in spite of all the efforts that scientists make to predict these important events. Well, so to sum up, uncertainty is something that we meet everywhere and it cannot be removed. It cannot be eliminated. But we are not satisfied with just stating that some processes has this feature, uncertainty. We take a step forward, and we observe that although a process may be uncertain in terms of outcome, some possible outcomes are more likely than others. Okay? If you take an exam, yes, there is some uncertainty as to the result, but if you are really well prepared, you can reasonably hope that you are more likely to be successful than not. Okay? If you start a new business, well, statistically, only 1 in 10 new businesses survives its first year. So if you believe the statistics, or rather, if you believe that this statistics refers to you too, then you must admit that you are more likely to be unsuccessful in your new business than successful. Okay? It doesn't mean that you should not try starting a new business. Well, each time I take the underground to get to work here, there is a chance that the train gets stuck under the ground and I miss my lecture. There is always this chance. We know that things like that actually happen from time to time, but I really hope that it doesn't happen to me, at least not in this course. Okay? Well, so what I want to say is this. Okay, a lot of processes have this uncertainty as to the outcome, but some outcomes may be more likely than others. Okay? And probability is exactly about this. Probability is a quantitative measure of likelihood. Okay? So, probability quantitative, oh, I'm sorry. My spelling is not very perfect, especially when I write on this whiteboard, quantitative. Well, basically, probability theory assigns certain numbers to possible outcomes, and these numbers are supposed to reflect, express this relative likelihood of the various outcomes. All right, some history now. Well, in the 17th century, some French mathematicians, including 2 famous mathematicians, Pascal and Fermat, started solving regularly the kind of problems that we now would call probability problems. It's curious to note that the motivation for doing this was not exactly of a noble character. The history has it that these mathematicians were approached by some rich individuals who were engaged in gambling, games of chance. Such as card games and roulette. So some rich individuals approached these mathematicians and sponsored their research into problems of this kind in the hope to develop a winning strategy. And this was the beginning of the probability theory. Okay? Also, Isaac Newton was also requested to solve some problems of this kind, although for Newton it was imaginary kind of activity, only a short experience. He had only a short experience in that. And I want to comment on this name, especially. The fact that Newton also solved some probabilistic problems can be called a paradox, because Newton was the father of so-called classical mechanics. And classical mechanics is a science that leaves no room for chance, no room at all. In classical mechanics, we assume that we can know the initial positions and velocities of all the bodies of the system that we observe. And once we know this, we can determine, using the equations of classical mechanics, we can determine the future, the state of the system for any point in the future. And there is no room for chance. There is no such thing as chance in classical mechanics. And Newton was exactly the founder of this science. Classical mechanics was a great achievement of science, and it explained a lot of things in nature. And for a couple of centuries, many scientists believed that this is the ultimate science. It can explain everything. Only in the 19th century, when thermodynamics was developed, it became clear that large aggregations of particles, such as gas, are subject to some additional laws, some laws that are not really reducible to the classical mechanics. So it was found that classical mechanics is not really good to explain everything. And early in the 20th century, quantum mechanics was discovered. And in the quantum mechanics, uncertainty is part of the basic equations. It's not something that can be removed. It's integrated in the basic equations. So it was found that uncertainty is really part of universe. And it's an integral part of the very foundation of universe. All right. But nevertheless, Newton had his hand in doing some probability theory. Getting back to this history, in the 17th century and in the 18th century, this early work was continued by Bernoulli, Gauss, and Laplace, and a lot of other brilliant mathematicians. In the second half of the 19th century and in the 20th century, a great contribution to probability theory was made by Russian mathematicians, including Chebyshev, Markov, and Kolmogorov. Okay. Well, also in the 20th century, the probability theory received a lot of important applications, such as the queuing theory, the decision theory, and game theory, and a lot of other important applications. Well, statistics. Just a few words about statistics. Well, actually, statistics has always been there in some form. Every state, since ancient times, every state needs to have information about its population. So since ancient times, governments used various methods to collect and process the information about the population, demographic data. But for many centuries, the methods for collecting and processing this data were of purely practical nature, rather than scientific nature. It was rather a practical art, not a science. And the methods used were what we now call methods of descriptive statistics. Okay? But there is, and descriptive statistics is about taking a complete census, complete record over the entire population, and then compressing the data in such a way as to make the information usable. But there is another kind of statistics. It's called inferential. quite often it's not possible to take a complete census. Then the only approach that can be taken is to take a limited sample and then use the data obtained on the sample to make conclusions or inferences about the entire population. This is called inferential statistics. Well, in the 18th century and in the 19th century, the methods of inferential statistics were mostly intuitive, but in the late 19th century and in the 20th century, a very important thing happened. Inferential statistics was integrated with probability theory. And probability theory provided a solid scientific foundation for the methods of inferential statistics. And inferential statistics. And this name is used today, and also as well as mathematical statistics. Inferential statistics and mathematical statistics are used as synonyms. Some important names in this history: Galton, Pearson, Gossett. These are the people who actually made this revolution. They converted this intuitive science of inferential statistics into a mathematical science. All right, in brief, this is the history of probability theory and statistics. All right, and now we really get to business. We start our discussion of the methods of probability theory. Now, what is the approach of probability theory to uncertainty? Probability theory copes with uncertainty by introducing a probabilistic model. Okay. Now, the first element of a probabilistic model is the definition of experiment. Okay, now, experiment in probability theory means something, it doesn't mean the same as in physics or chemistry. In probability theory, experiment is a very broad concept. Experiment in probability theory is anything, any process or activity that is subject to uncertainty, that has an uncertain result. Okay, so for example, just to avoid confusion, suppose you observe the fluctuations of exchange rate of dollar to ruble. You don't feel that you can influence it in any way. So it's not a kind of experiment that you stage and you control. You have no control over it. What you can do is just observe what happens. Okay, and still this kind of activity is called experiment in probability theory. All right. The next thing is to define is sample space. Sample space. And the sample space is the set of all possible outcomes. Set of all possible outcomes. Okay? Well, if you think of it, this is not a trivial thing to say. Here we assume that we can define the set of all possible outcomes. We know what can happen. Okay, this quite often it's simple, sometimes it's not. But in probability theory, we assume that we know the set of all possible outcomes. Some very simple examples. Why? Well, the simplest and the most traditional example in probability theory is the experiment of tossing a coin. Okay. Is it an experiment in terms of probability theory? The answer is yes, because we don't know the outcome. How many outcomes are there? What is the sample space? The sample space contains only 2 outcomes. Okay, set of notation. Well, this is the standard way to denote the sample space. It's the capital Greek letter omega. Omega. This is the common notation for the sample space. And what's the sample space for the experiment of tossing a coin? It's this set, heads or tails. Okay. The coin turns up heads or it turns up tails, and there are no other possibilities. Okay, that's it. Simple. Well, the next classical example is rolling a die. Rolling a die. Well, meaning a six-faced die. Okay, there are dice with a different number of faces, but we talk about this most common type of die, that the one that has 6 faces, and and this is the sample space. Okay. The next classical example is drawing a card. Well, usually, as an example, we use this standard 52-sheet card, 52-sheet deck, a deck of 52 cards. Well, I'm not going to list all of them. I just want to mention that there are 4 so-called suits. Do you know what suit is? Well, the 4 suits are spades, diamonds, hearts, and clubs. Okay, and each, because we have 52 cards in total, 52 cards in total, each suit contains 13 cards. Also, there are denominations. Okay, from 2 to ace, and there are 13 denominations. Okay. Again, simple enough. And but if we draw a card at random from a standard deck, the complete list of outcomes has these 52 possible outcomes. Well, if you start a new business, okay, well, actually it's up to you how you define the sample space here. You may be interested in knowing whether you are going to fail or succeed within the first year of this new business. Success or failure within a certain given period of time. But I want to use this example to note that the definition of omega is actually up to the observer, and the definition of sample space reflects the interest, the kind of interest that the observer has in this experiment. Because apart from defining the sample space here in this way, you can define it by adding another possibility, the possibility that your business not only succeeds, not only survives the first year, but brings you your first million within the first year. Okay, it's also a possibility, and you can be interested in including this into the list of possible outcomes. Okay, this is just an illustration that omega actually depends on the standpoint that you take. All right, any questions here? Just very simple examples. All right, now so we start with defining experiment, then we define the sample space, and the next step is this. The key term and the key notion in probability theory is that of event. Actually, an event by definition is any subset of omega any subset of the sample space. And in other words, an event is any collection of outcomes for the given experiment. Some very simple examples. For example, we rolling a die. Well, let's define event A as getting 1. Okay, is it an event? Yes, of course. This event contains just one outcome, one element, and it's 1. So any outcome is also an event. B. Well, 1 and 2. Okay, like this. 2 elements. C. Well, rather than listing the elements here, I prefer to give a verbal description. So the event C is defined as getting an odd number. How many outcomes are contained in this event? 3, it's 1, 3, and 5, okay, obviously. And the event of getting an even number also contains 3 outcomes. D. The event of not getting a 6. How many outcomes does it contain? 5, obviously, 1 to 5, okay? The event of getting a 7. How many outcomes? None at all. None at all. It's an empty set, and this is an accepted notation for an empty set. So this is an empty set, but it's also an event. Okay, this is a legitimate definition. We can define an event in this way, but then we know that it's an empty set. Okay, well, quite often a useful visual tool is used to illustrate different situations in probabilities. And it's called Venn diagrams. Venn diagrams. In a Venn diagram consists of a large rectangle that represents the sample space. And then any event that we're interested in is represented by, well, by a circle, or maybe some other shape that we want to use that is contained in this omega. Okay, so this is an event, some kind of event. Okay, it's not a big deal. It just helps us to get an intuitive idea of what we are dealing with. Okay, all right. Now, probability. What is probability? Now we are ready to answer this question scientifically. Probability is, so we have defined an experiment, okay, and we have defined a sample space for this experiment. This being in place, these two things being in place, we are ready to define probability, and probability is a function defined on the set of events for the given sample space. Okay, so let's probability is a function defined on the events of the given sample space, but not just any function. To qualify as probability, this function must satisfy a certain set of requirements called axioms of probability. And these axioms were introduced by the Russian mathematician Kolmogorov, Andrei Kolmogorov. Well, there are 3 axioms actually. Now, notation. The accepted notation for probability is a capital letter P, capital P. Okay. Now, what's written here is this: the probability of any event E is non-negative. It can be 0, but it cannot be negative. Okay. Axiom 2. If A intersect B is an empty set, which inverts is referred to as okay. If the intersection of 2 sets is an empty set, then the term used is this. We say that the 2 sets are disjoint. Okay? If we specifically talk about events, this other term is also used, mutually exclusive events. So, if 2 events A and B are disjoint or mutually exclusive, then P of the union A union B is just the sum P of A plus P of B. But please pay attention to this condition. If two sets are not disjoint, this formula is not true. And the third axiom is this: P of omega is 1. Actually, this is an arbitrary condition. We could select any other number here, such as 100, and the theory would work quite as well. But we need to introduce some number, some standard number for the complete probability of the entire sample space, and here it's 1. This is the accepted. It's called normalization condition. Okay, now it's time to mention the three possible ways to introduce probabilities. We have, okay, like this. We have done some preliminary work. We have talked about experiment and sample space and events, and we have agreed on what we understand by probability, and we introduced these requirements, these axioms for probabilities. But you may ask, where do we get any probabilities anyway? What is the possible source of these numbers? Okay? And this is a very important question, actually. And there are 3 possible sources. One is the so-called classical, let's call classical model. classical model. Now, this model works and works very well if we have a sample space that is finite. This is condition 1. And it's made up of equally likely outcomes. So, this is finite sigma of equally likely outcomes. Well, unfortunately, these conditions are not always met. Quite often we have to deal with sample spaces that are not finite. And even if they are finite, quite often we have reasons to say that the outcomes are not equally likely. Well, life would be beautiful if these conditions were always valid, but they are not. Okay, now let's assume that these two conditions are satisfied. Then the probability of any event E is defined as this quotient. Okay, n small of E divided by n capital, and here n capital is the number of outcomes in omega. That is the total number of possible outcomes in this experiment, and this is the number of outcomes in E. Okay. Well, as I mentioned earlier, I can't go into proving all the statements that I give you here, but just, well, as an exception, let's discuss the proof of this one. Actually, we can prove that it should be this way. We can prove that it should be this way, that the probability... do you have a question? No? We can prove that this formula should work if these axioms are valid. Let's do it. Omega is assumed to be finite. It's assumed to contain a finite number of outcomes. So we can write this. Omega is, or rather, okay. This is also omega. This is the little letter, Greek omega. What I write here means this. Omega consists of these possible outcomes. Okay? Outcome 1, outcome 2, outcome 3, and outcome n capital. And the next step is this. All these outcomes are mutually exclusive. Outcomes always are, by definition, mutually exclusive. So the probability of omega, which is by axiom 3, it's 1, must be equal to the probability of this union omega 1, omega n capital, like this. Okay? And because they are mutually exclusive, it must be the sum of the individual separate probabilities. Okay? So we have used this condition, finite omega, and now it's time to use this other condition, that the outcomes are equally likely. So in this sum, all the terms are the same, actually. And using this, we can write it this way. Okay? So this is n capital multiplied by the same number. And this must be equal to 1, from which the probability of each outcome is 1 over n capital. And then we notice that E contains n lowercase outcomes, all mutually exclusive. So E, the probability of E must be equal to n lowercase of this, and times this. Okay, like this. Any questions? Well, it's not a big deal. It may seem very simple, but let me tell you that statements like this and proofs like this are really fundamental. All the rest follows from this stuff. All right, any questions here? Did you notice that we actually use these two conditions, finite omega and equally likely outcomes? If at least one of them were not valid, we would not be able to do this, and this formula would not work. Okay? All right. Well, some very simple examples. I think it's time for me to do some erasing work. Okay. Well, some examples of the classical model. Tossing a fair coin. Now, do you notice a new word here? I don't write tossing a coin. I write tossing a fair coin, which is essential. By stipulating this, I say that the two outcomes of this experiment are equally likely, which is quite natural to assume if the coin is symmetric. Okay? If it's symmetric, we have no reasons to believe that heads is more likely than tails or the other way around. Okay? So and this is called fair coin. Okay, now the probability of getting heads. Using the formula, the number of outcomes in the sample spaces is 2, and the event of getting heads contains only one outcome, so it's 1/2, and 1/2 for tails. Very simple. Now let's roll a die. Rolling a die. What's the event of getting an even number? Sorry. Well, how many outcomes are contained in this event? 3. The answer is 3, and the total number of outcomes in omega is 6, so the answer is 1/2. Okay? Well, see. Suppose in a student group there are 20 girls and 10 boys. Okay, like this. And suppose a teacher selects one student at random to do a certain assignment, okay, a certain project. And if the choice is made if it's a random choice, then what's the probability that the person selected will be a boy? Well, it's again, it's probability of getting a boy is 10 over 30, which is 1/3. Okay, simple enough. This is how it works. But please notice that here we assume that the rolling rolling a fair coin, and and the die here is assumed to be fair. I'll not be repeating this each time, okay? Whenever we say that we roll a die, we always assume that it's fair. And here, okay, please tell me which words that I said when I introduced this problem mean that the outcomes are equally likely. Random. The word random means exactly this, okay? I said that it was a random choice. All right, I think this is simple enough. Another principal approach to introducing probabilities is experimental. Now, let me tell you that this classical model is really beautiful. It allows us to compute many probabilities, some of them not intuitively, well, not easy to get at intuitively. And this is a beautiful theory. The only disadvantage of this theory is that, unfortunately, this assumption that the outcomes are equally likely almost never works outside games of chance. Okay? Games of chance is where it works, and unfortunately, it's very seldom that this condition is met in other areas. Okay? Well, experimental approach. Well, imagine that you have a coin that is not fair. You know in advance that it's not symmetric. Okay? Let me tell you that it's a very difficult problem for classical mechanics to compute what is the probability of it turning up heads or tails. So if we step outside of this classical model, we're helpless. We don't know what to do. If a coin is not fair, or if a die is not fair, we don't know how to compute the probability of getting heads or tails, or 1 or 2 on the die, and so on. Now, what can we do about determining these probabilities? Suppose you have a coin that is not fair. Actually, the word is biased. Biased means not fair. What you do is perform a long series of experiments. You can toss this coin a very large number of times and then record carefully the number of times it turns up heads. Okay? And then this is called frequency. Suppose you perform the same experiment n capital number of times. Okay? And then you count the number of times that event E that you are interested in occurs on n repetitions of this experiment. Okay? This is called frequency, and by dividing it by n capital, you get the relative frequency. And then you ask this question. Suppose you increase the number of repetitions of the same experiment indefinitely. What happens to this relative frequency? Is it going to stabilize at some limit? Okay? This is a big question. And this question cannot be answered logically. It's a question, an answer to which is given by the universe, okay? And let me tell you that experiments like that have actually been staged a lot of times, and it was found, it has been established quite reliable, in a very reliable way, that if the same experiment is performed a very large number of times, relative frequencies do stabilize at some values. And this is a fact of nature. It's not, again, let me emphasize that it's not something that we deduce logically from something else. It's an experimental fact. Actually, it's an experimental fact of fundamental importance. So these limits do exist. And in this way, at least in principle, we can get probabilities. So an experimental way to introducing probabilities is this. Perform the same experiment very many times and look at the limits, limiting values of relative frequencies. All right, and this is also a very good approach. Unfortunately, not all experiments can be repeated. Okay. Just in this past year, this natural phenomenon occurred, the fall of meteorite somewhere near the city of Chelyabinsk. Okay? This is an experiment. In terms of probability theory, it's an experiment. But can you think of a way of reproducing this experiment? We can't reproduce it even one time, not to say nothing of reproducing it 1,000 times. Okay, it's just a unique experiment, a unique event that we can only observe once. And if you think of it, many of the things that we're interested in are of this nature. They only happen once, and they cannot be reproduced. So this model, experimental model, although it's beautiful, it's quite productive, also have rather limited application. Well, what can we do if the classical model doesn't work and the experimental model doesn't work either? What we're left with is subjective probabilities as given by experts. Well, whenever a football match or a hockey match or any other sports event takes place, bookmakers come up with certain ratios, that can be used to make bets. Now, these ratios are founded on subjective estimates of probabilities of what's going to happen. Now, because bookmakers are responsible for this in terms of paying their own money, their estimates tend to be very accurate, but quite often they turn out to be false. So this is the best an expert can do. If an expert pays his own money for the outcome, then typically estimates are very good. The best that can be done. But unfortunately, they are not always true. So this is an expert approach. All right. Now let's mention some consequences of axioms. Some consequences. Okay. Using the axioms, we can prove that the probability of any event is less than or equal to 1. One of the axioms is that the probability of omega is exactly 1. But this is something else. This tells us that the probability of any event cannot exceed 1. And this can be proved from the axioms. Then the probability of the empty event is 0. And also this. If, well, suppose A is contained in B, contained or is equal to B. Do you understand this? Suppose all the outcomes that are contained in event B are also contained in, all outcomes that are contained in A are also contained in B. This is what's written here. If this is true, then the probability of A is less than or equal to the probability of B. Okay. Also this. Now let's use this notation for complementary event, complement A. Now, complement of event A. Now, what does this mean? If this is A, then complement A is everything and anything that is outside A. Okay? So all the outcomes that are not contained in A form complement A. Now, quite often in textbooks, this notation is used. C for complement, but it's not very convenient when you write on the blackboard or whiteboard. So I'll keep to this one. It's also an acceptable notation. All right. Now, A and complement A are mutually exclusive. Okay? So A and complement A do not have any outcomes, any elements in common. Okay? This is point 1. And point 2 is this. Put together, A and complement A form omega. So what we have, the conclusion that we get is this. Okay, like this. Well, and let's give it an example. Well, suppose we toss a bias coin 10 times. Suppose we know somehow that the probability of getting heads for this coin is 0.6, not 0.5. And we toss this coin 10 times. Now, what's the probability that we get tails at least once? Tails at least once. Okay. Well, one way to do this, to answer this question, would be to think of all the different ways that we can get at least one tails. Well, tails at least once on 10 tosses. Well, it's not a simple job to do. But we have, this formula gives us a very effective alternative approach. We can say this. The probability of tails at least once. Now let's ask this question. What's the complementary event? What's the complement of this? Well, the event that we're interested in is getting tails at least once. The complement is getting heads 10 times. Okay? So we can write it this way. Plus probability of 10 heads. These two must add up to 1. Okay? Now, is it any easier to get this probability? What's the probability of getting heads 10 times in a row if getting heads on one toss is 0.6? Well, this is a question that we are not quite ready to answer at this point, but we will do it just in a very short while. And the answer is 0.6 to the power 10. Okay? We'll get to this stuff in just a short while. So the answer to our question is this. It's 1 minus 0.6 to the power 10, and using the calculator, the answer is this. Okay? Let me tell you that we have already computed something that is not at all intuitively clear. Our intuition is not good enough to answer questions like this. This is an exact answer to this question. All right. Now let's consider a more general version of this equation. Now, suppose we have any two events, A and B. any two events. Let's consider these two. A intersect B and A intersect complement B. Okay? Let's use the Venn diagram. This is what Venn diagrams are for. They help us understand what we are talking about. Suppose this is A and this is B. Then what is this? It's this section in the center, A intersect B. And what is A intersect complement B? It's the remaining portion, A intersect complement B. Well, do you understand this? Okay. Now let's notice two things. First, these two events, A intersect B and A intersect complement B, are mutually exclusive. No elements in common. And put together, they form A. So the union is A, the intersection is null. Okay? Which leads us to this formula. P of A intersection B plus P of A intersection complement B is P of A. Okay? Well, now this formula can be used to solve quite efficiently problems that involve two events. Scheme for solving two event problems. Okay, I'm not sure this is a standard name for this technique. It's a name that I propose. All right, what are we talking about here? We compose a table. Suppose we have two events. We are trying to solve a problem that involves two events, A and B. Then we form this table. This is A, this is complement A. This is B, and this is complement B. And then what I fill in here is this. Probability of A intersect B. Probability of complement B intersect, complement A intersect B. Probability of A intersect complement B, and probability of complement A intersect complement B. So 4 probabilities. And now let's do this. Let's sum up these two. Probability of A intersect B, probability of A intersect complement B. Using this formula here, let's enclose it in a box to emphasize its importance. Now, this is P of A, probability of A. Okay? Now, and this is probability of complement A. And now let's write this capital Greek sigma to remind ourselves that we sum up. This last row contains sums. And also we write sigma here, and we perform summation along rows now. So what's the sum of these two? It's P of B, and the sum of these two is P of complement B. Okay, and what's the sum of these two? It's 1, same as the sum of these two. Okay, now look at this. How many probabilities are contained in this table? 1, 2, 3, 4, 5, 6, 7, 8. 8 probabilities. But because of these known relationships that connect them, only 3 of them are independent. If we know any 3 of these 8, we can easily compute the other 5. Let's give it an example. Okay. Let me use my figures here. Now, in a certain population, 25% of the members are known to drink tea. So in a population, 25% drink tea. Okay, and also 15% drink both tea and coffee. Both tea and coffee. Okay. And 30% drink neither tea nor coffee. Neither tea nor coffee. And the question is this: suppose we select a member of this population at random. What's the probability that he or she drinks tea? Probability that this member, randomly chosen, drinks tea. Okay? Well, of course you can do without this technique. You can figure it out somehow. Maybe Venn diagrams can be used here. I think they can. But this table gives us a very efficient way to solve this kind of problem. Now let's produce a table like this here. And it's going to be this. Okay. So tea, complement tea, coffee, complement coffee. All right. Now, what do we know? What are we given here? 25% drink tea. Okay, and this is here. So if we select, if we choose a person at random, there is this probability that the person is a consumer, a regular consumer of tea. Well, 15% drink both tea and coffee. I'm sorry. I'm sorry. Can I make a correction here? I have a slight confusion here. Now let's say that it's coffee. Coffee. I'm sorry about this. Otherwise it doesn't make sense. I already supplied you with the probability that somebody drinks coffee, and the same question is put here. So 25 chance that they drink coffee, and then we enter this number here. Where do we enter this number? Both tea and coffee is entered here, and neither tea nor coffee is entered here. And where do we put the question mark? What do we want to know? The probability that a randomly chosen person drinks tea. And this is the cell that will contain the answer here. Well, and how do we cope with this? What can be computed directly in one step, given these data? Look at this first row. This number plus this number, which is not known, must make 0.25. So we conclude that this cell contains 0.1. Okay? Well, now this number and this number add up to 0.4. And by the way, what is this? What is this number here? What question does it answer? It answers the question, what is the probability that a randomly chosen person does not drink tea? Okay? Now, this cell that must contain the answer to our question, plus this cell must add up to 1. So this cell contains 0.6, which is the answer to this. Okay? So, in a matter of seconds, we solve this problem, which is not very easy if you don't have this technique. Okay, please pay attention here. Some cells here are left blank It doesn't mean we cannot get these numbers too. It's easily to get this and that. We just don't need them to answer the question that is posed here. The next big question for us is the addition rule. Addition rule. What's the probability of A union B? Let's use this technique and diagram. Okay, what is A union B in this picture? It's this total shape, okay? And what probability should be assigned to A union B if a probability of A and probability of B are known? Is it P of A plus P of B? P of A plus P of B. Is it true? Well, the answer is no, it's not true. But I want you to see the reason of why it's not true in this picture. The problem is this section, A intersect B. If we just add up P of A and P of B, the probability of this middle section will be counted twice. And this is the problem. Okay? So the right formula is this: P of A plus P of B minus P intersect B. Well, it can be proved rigorously, but I'd rather not spend time on this. I rely on your intuitive understanding of this. So to avoid overcounting, to avoid double counting of this middle section, we need to subtract P of A intersect B. Okay. Well, just as a simple example, well, suppose we have two football teams. One of which is called Lions and the other is called Bears. Okay? Very powerful names. And the bookmakers say that the probability that Bears will get to the final, Bears get to final is 0.4. And the probability that the Lions will get to final is 0.5. Okay? And also, some experts say that, I'll continue here, the probabilities that Bears and or Lions get to final is 0.7. Okay, so we have these three expert estimates of probabilities. And the question now is this: what's the probability that both teams will get to final, that the final match will be played between these two teams, Bears and Lions get to final? Okay, what's this? Okay, now let's look at this probability here. It's the union of two events. Bears get to final and Lions get to final. By this formula, it must be equal to the sum of the two separate probabilities, these two, minus the probability of the intersection. So it's going to be 0.4 plus 0.5 minus this one, minus what we are interested in, okay? This one. From which, solving this simple equation, we get this answer. The probability that the final match will be played between these two teams is 0.2. Simple enough, okay? Well, this is the general formula for adding probabilities, for computing the probability of the union of two events. But it has this particular case, well, for the mutually exclusive events A and B, this term is absent. Okay, if A and B are mutually exclusive, we have this simplified version of the formula. Okay, simple enough. But we must be careful. We need to always to ask ourselves this question: are there events that we are dealing with mutually exclusive or not? It's easy to make a mistake. Okay, let's consider this very simple example. Suppose you are going to take an exam in probability and statistics, and you estimate your own chances of getting an excellent mark. So, probability excellent okay. And this is your own estimate of getting an excellent grade. Probability of getting a good grade are estimated at, okay, you must be a good student actually, because this is not a small number. And probability of a satisfactory grade, you estimate at 0.3. Now the question is this: what's the probability that you fail? Okay. Well, first let's answer a different question. What's the probability that you do not fail? What's the probability that you pass? The probability that you pass is the sum of these three, because you pass when you get a satisfactory mark, grade, a good grade, or an excellent grade. And this is the sum of these three plus 0.3, and they add up to 0.6. And now we can easily answer this question. The probability that you fail is this. Well, by the way, this is a very realistic number, because roughly 40% of my students fail this exam. All right, do you notice where we use this assumption here, mutually exclusive? Okay, we use it here. Now, these outcomes, satisfactory mark, a grade, good grade, an excellent grade, are mutually exclusive. You can't get a good grade and an excellent grade at the same time. If they were not mutually exclusive, we would not be able to use this simple sum, okay? All right. Now we still have some time left, and because I'm in this great hurry, I want to start the new topic, which I'm going to pick up next time. And the next big topic is conditional probability. Okay. Now let's discuss this simple example. Example. Well, in a student group, there are 14 boys and 16 girls. 6 of the boys practice some sports. 6 boys practice sports. And 4 girls practice sports, okay, like this. Well, first we ask a preliminary question. Suppose a member of this group is chosen at random, what's the probability that he or she practices sports? Okay, well, it can be easily answered if we first compute the number of students that practice some sports, and this is given by adding up these two numbers, so it's 6 plus 4, and we're divided by the total number of students in the group, which is 14 plus 16, and this is 10 over 30, or 1/3. But this is not the question that we want to answer here, it's just a warm-up. Well, the real question that we ask is this. Suppose a student is selected at random. What's the probability that this student practices sports given that it's a girl? Okay. And please pay attention to this notation. This is an accepted way to denote things like that, probabilities like that. What's the probability that a randomly chosen student practices sports, and this vertical bar, vertical line, and then this is a condition, given that this student is a girl. How do we answer this? Well, it's easy to, well, let's look separately at the girls, because, well, here we are told that the student is a girl. There are 16 girls in total, and 4 of them practice sports. So if the student is chosen at random, the probability must be 4 over 16, which is 1/4. Please pay attention, it's not the same as this one, okay? And it shouldn't be. We do not expect it to be the same answer. Now we are looking at girls only, not at all the students here. But I want to do something else. Well, let me comment here. If we are given this condition, effectively, we begin dealing with a different sample space. We no longer deal with the sample space of all the students here. We only look at the girls. So the sample space reduces from 30 to 16. Okay? We kind of solve a problem with a different sample space now. But if we return to the old problem, we can express this probability in terms of some probabilities referring to the old problem. And this is how we can do it. We can divide 4 over 30 and 16 over 30. Arithmetically, it doesn't make any effect on the answer. What does it, what useful, what's the use of this division? Writing it this way, we now can interpret it in a certain useful way. Now, look at this denominator here. Can you interpret it in terms of probabilities? 16 over 30. Can you assign some meaningful probability to this number? There are 16 girls in the group, and 30 is the total number of students in the group. So 16 over 30 is the probability that a randomly chosen student is a girl. Okay? So this denominator is the probability of choosing a girl if you choose a student at random. And look at this numerator now. Can you explain it in terms of probabilities? 4 over 30. What is 4? What?
Girls who practice sports.
Girls who practice sports. Okay? So 4 is the number of girls who practice sports. And if you select a student at random out of the total number of 30, this is the probability that the selected student is a girl who practices sports. So we write it this way. This is girl and sports. Okay? It's a joint. It's the probability of intersection, girl and sports. Okay, and this gives rise to the general formula. The probability of event B, given that event B, probability of event A, given that event B occurs, is this: A intersect B, B. So we start with this simple example that is that actually belongs to the classical model. Please pay attention to this. So within the classical model, this is a very simple stuff. This kind of question can be very easily answered. But now we go outside the classical model and just introduce a definition. This is a definition. This is a definition that will be applied to all kinds of probabilities, and this is the definition of conditional probability. Thank you for your attention. See you next time.